final talk of the first day by Frans Pretorius.
Okay, thank you, and thank you very much to the organizers for inviting me. It's great to be back here in Cambridge and at the Isaac Newton Institute. Okay, so I'm going to talk about computational challenges in numerical relativity, sort of as the overriding theme, and then sort of as a subtopic to illustrate some of this, this background error subtraction technique and an application to black hole superradiance. So I know this is a very broad audience, and either we're going to be several. I think so. Perhaps let me put it a bit higher. Hello. It's on over here. The light. Okay, can everyone hear me okay? I think the battery might be a problem. The light is going off here. It turns off. Yeah. Oh, is that good? Okay. Okay, so as I said, yeah, I knew it's going to be a broad audience and there are going to be several talks before me, so I wasn't quite sure how much introductory material to give. So I've got a lot of slides, and I'll go over the introductory material, and I'll try to just rephrase it in a way that's slightly different from some of the speakers this morning. Okay, so here's an outline of the talk. So I'll give a brief overview of computational general relativity, and just roughly what the problems are, and some of the challenges going forward. And then as a motivating problem, I'll talk about black hole superradiance, which is essentially scattering a wave off a black hole, a rotating black hole, and the emitted part of the wave, or the wave that goes back outwards, has larger energy and angular momentum than the incoming wave. And I'll mention this background error subtraction algorithm that is designed to solve sort of a very small sliver of, let's call it solution space, of the open challenges. So as we heard about today, like one of the big problems is the large range of spatio-temporal scales that typically develop. And here, if it happens to be that your solution is dominated by a known exact solution, then you can subtract off the truncation area in a way which allows you to very efficiently resolve the problem. So I'll describe that. If I have time, I might also describe the original motivation that Will Easton had for developing this problem, and that's the tidal disruption of a star by a black hole. But then I'll describe the application to gravitational wave superradiance. So again, my apologies to perhaps the numerical relativists in the audience that some of them might have heard everything that I'm going to say. Hopefully some of you weren't at all of these the talks, so there might be something interesting for everyone, I hope. Okay, so let's just recap again what has been gone over a few times today already. So numerical relativity is concerned with solving the Einstein field equations, here written in its usual very nice tensor form. The Einstein tensor is proportional to the stress energy tensor, Newton's constant, the speed of light. But what we really want to know, and I'm going to, again, like most people, not worry too much about the matter. Knowing the matter evolution is interesting, but perhaps the main problem with these equations is the geometric side, the Einstein equations. So we trivially know what the Einstein tensor is, but what we really want to know is what the metric tensor is. We want to understand what the geometry of space-time is, and so that means we want to know what the metric tensor is by solving the Einstein equations. And so this, in a nutshell, sort of tells you like why it's such a challenging problem. So again, I'm using the Einstein summation convention, and as I've inferred from the previous talk, that's also common notation here, so it will be familiar to everyone. So if you know what the metric tensor is, it's very easy to compute the Einstein tensor. It's just differentiation, essentially, differentiation and summation. So taking the metric tensor, we compute these first gradients. So I'm using commas to denote ordinary derivatives. We do the summation, we compute the connection, or the Christoffel symbol. We take gradients of the Christoffel and quadratic sums of these. We compute the Ricci tensor, the Ricci scalar, and then we get the Einstein tensor. So of course it might be a tedious thing, but it's straightforward going from one to going in this direction. But of course we want to do the opposite. We want to, given the Einstein equations, we want to solve for the metric. And so just following through, you can see what the Einstein equations are, and you're in 4 dimensions, It's a symmetric tensor, so 4x4 matrix, if you will, but 10 independent components. And so what you get at the end of the day is a system of 10 second-order quasi-linear partial differential equations for the 10 components of the metric. And it's quasi-linear because essentially the non-linearities come in lower-order terms. So these essentially encode the non-linearity, so they only involve first derivatives of the metric. So it's a complicated system, but it's at least that's at least one thing going for it. It's not fully nonlinear in that sense. Okay, so what are we interested in applying it today? And so we've had a few really interesting talks. First by Deirdre, some sort of mostly focusing on the astrophysics-motivated topics. And primary among those are understanding the collision of compact objects. And thanks to the effort by the gravitational wave community that sort of built these astonishing detectors, now in the last few years we've been able to observe binary compact object collisions in the universe. And it's really just a very new sort of astronomical multi-messenger field. And I think the next few decades is going to be, I think we're going to see a lot of interesting discoveries, not just coming from LIGO, but some of the future space-based detections, or space-based missions, and the corresponding connection with electromagnetic and neutrino emission. Then on the other side, what Powell sort of very nicely described is what I'm just calling here theoretical gravity, and whether it's open questions sort of in classical relativity, critical phenomena at the threshold of black hole formation, the nature of singularities, ultra-relativistic collisions, or higher dimensional gravity. I think there are many interesting open questions there that aren't necessarily motivated by astrophysics, that are still that are open and that are amenable to numerical solution. So what are the main problems? I'd say, so I've written here sort of major issues, and so these two, the first 2 points, people have sort of gone over them. People have actually gone over all of these points, but these first main two points I think are to some extent solved, and that is one, the mathematical ill-posed character of the equations if you take them verbatim, and how to massage them and come up with formulations that are sort of amenable to a well-posed discretization and that controls the boundedness of the constraints. So as Powell mentioned, there are a few methods where I would say this, for at least for a large class of problems where it's been tried, has solved this problem. So the BSSN, the ZZ, C4 generalized harmonic forms, and they've also shown that how to control the growth of constraints from truncation error. The other problem, and that's also been alluded to at several of the talks, is just the computational cost of solving these equations. And it's not just because they, thousands of terms when you do the sums. It's because the interesting problems that we want to go after have a large range of relevant spatio-temporal scales that need to be resolved. Now, the other difficulties, which I'd say are somewhat minor, but they also complicate, perhaps unique to the field equations, and the fact that we're dealing with space-times with singularities inside of black holes for the most part, and what might especially be important for some of these sort of non-astrophysical problems where we're sort of going into uncharted territories is how to find proper gauge conditions or coordinate conditions to evolve enough of the space-time to get the answers that we want to go after. Okay, so what are the properties of sort of typical solutions, and sort of how do they impact, or how might they impact solution methods or computational costs? So one thing is bad is that the theory has singularities, so those are problems that we have to deal with. On the other hand, at least in 4D, where we know, well, it seems like cosmic censorship might hold, and cosmic censorship roughly is just the idea that the singularities occur, but they're hidden behind event horizons. And so what that means is if we want to predict all of the physics outside of event horizons, causality protects us from having to know what happens at the singularity. We don't need a theory of quantum gravity to solve singularities. So you worry with like nonlinear equations, like what are all the problems that could develop? Singularities could develop. In hydrodynamics, you could have shocks, things like that. But it turns out that in the cases that the people have looked at, all those other pathologies that show up in Navier-Stokes, for instance, they're not present in the Einstein equations. So we don't get shocks. Solutions are typically smooth away from singularities, and the singularities occur in a way where we can sweep them under the horizon, so to speak. And perhaps one way to think why that's the case is if you just go back to the Einstein equations. So even when you couple to matter which does have shocks, surface layers or the surface of a planet, typically to get the metric which we're going after, we have to integrate twice. So it sort of smooths out features of the matter, and somehow the structure of the Einstein equation says is that those kinds of things don't develop in the metric by itself. Right, and that's also especially like one of these things, dynamical coordinate conditions, especially thinking of going to new problems where we haven't yet figured out what to do. If we run into a coordinate singularity or a coordinate shock or something like that, that's a real problem, yeah. Okay, and then the other thing that also the people have mentioned today is, even if we don't have to worry about these things, problems are expensive because they typically involve a wide range of length scales, but both in space and time. And so, this example was also brought up today. For example, the binary merger problem. Thanks to excision, all the small scale stuff that can happen inside horizons we can get rid of. So we really just have to resolve the horizon, which in our units is of order the mass. It's linearly, the size of a black hole is linearly related to the mass of the black hole. So we usually use units of mass to rescale all of our lengths and times. So that's the smallest scale that really needs to be resolved. But then there's an orbital scale that needs to be resolved. That's roughly 10 times that. You can't measure gravitational waves unambiguously close to the system in the near zone. You have to go to the wave zone, which is another order of magnitude beyond that. And also you need to put the outer boundary a little bit beyond that to avoid issues from the outer boundaries. So you're already sort of 2 to 3 orders of magnitude of length scales that need to be resolved. And that's for a comparable mass system. As Deirdre was mentioning, if we think of that sort of perhaps the next frontier going to mass ratios of 10 to the 2, 10 to the 3, that's adding another couple of orders of magnitude to this problem. And that's just the vacuum problem. If we think about, now we have mergers that involve neutron stars, say 2 neutron stars merging, and then once neutron stars merge, you have all turbulent dynamics of the matter taking place that introduce and microphysical timescales that sort of blow this length scale problem up by several additional orders of magnitude. Okay, so what are typical solution methods that have been used? So for whatever reason, I'm not sure if this is necessarily a good reason, just historical prejudice, finite element methods have not been used very much in the evolution scales, but finite difference and pseudospectral methods have been. They're pretty popular, so and method of line, sort of Runge-Kutta type integration schemes for time integration is also popular. And as Pao mentioned, in many of these problems, some form of adaptivity is essential, to get past a few of these orders of magnitude in scales, and some form of Berger and Oliger style adaptive mesh refinement is also usually pretty popular.
Is that Runge-Kutta just explicit Runge-Kutta method?
Yes, just RK4 is the sort of most common. Yeah, and perhaps sometimes they go a bit higher order, but yeah, it's just a very simple explicit Runge-Kutta. So even though it's like these things are incredibly computationally expensive, I'd say the relativity codes have not really been optimized to scale typically more than of order 1,000 cores. Like often you hear of some of these astrophysics applications and some other codes where they've scaled to the latest records of order millions of cores. I mean, we're not even close to that. I'd say in our defense, at least for the astrophysics problems, we don't really need to be that close to that because in some sense we've also got another dimension that we have to worry about, and that's sort of parameter space. So if you think we have to build waveform libraries to understand and interpret gravitational wave observations. So each one of them is we have to sample between the mass ratio, the spin vectors, the eccentricity of the orbit if we're interested in going after that system. So there's so many of these things that we have to do. It's fine if we had 1 million CPU cores, if we have to do 1,000 simulations, we might as well do them all simultaneously on a 1 million core system as opposed to doing them very rapidly on 1 million cores at one time. So there hasn't yet been enough of a need for us to do this. But I think going to certain other problems, and for instance, more on the line of the problems that Power was talking about, where we don't necessarily have to do such a huge survey of parameter space, where there might be one interesting problem where you want to it's just put a lot of computing time behind it. That would be something that might be useful to do in the future. And also, one thing is that very few codes have been, I should say none of the workhorse codes have actually been ported to GPUs, or none of the main results have come from GPUs. There have been case studies where people have shown that it's possible. And one reason, especially for the astrophysics motivated problems, the binary merger problem, is that the codes are very memory intensive, and you just can't fit it on a single GPU core. So you're going to have to distribute it across GPUs, and then you run into the inter-GPU communication bottleneck, and that essentially significantly cuts off the kind of potential performance increase you can get from using GPUs. So that's another thing that hasn't been done much yet. Okay, so that was a sort of very rough overview of some of the problems. And so perhaps the main takeaway is we have to deal with this length scale issue in something. We've got to come up with methods for the length scale problem. So now let me turn a bit to physics and black hole superradiance, just to describe it to those that aren't necessarily familiar with it, and then illustrate that this is one problem which also has its own length scale and time scale problems. And this is one where this background error subtraction technique can actually be used, and then I'll describe exactly what that is and then show you some results. So black hole superradiance it might sound exotic if you haven't heard of it before, but it's really, it's a phenomenon that's not unique to black holes. And perhaps the simplest analog example you can think is just a spinning wheel. So you take a bicycle's wheel, you spin it very rapidly, and now you throw a pebble onto the rim of the wheel. And if that sort of the pebble lands on the wheel, and at the point where it's landing on the wheel, it's going a lot slower than the spin of the wheel, the bounce, the wheel could impart extra spin, could give it a kick. And so if you look at sort of angular momentum relative to the center of the wheel, that pebble has gained angular momentum. The reaction on the wheel is the wheel will slow down a little bit. And that's basically black hole superradiance in an analog system. And so what happens with a black hole is we have a rapidly spinning black hole. You interact with it in the various ways in which this kind of process works out. The one that I'm going to talk about is just, so you implode a gravitational wave or some wave from some bosonic matter field onto the black hole. The black hole is spinning fast. The wave that you implode onto it also has a spin, but it's going slower than the black hole space-time. And so in this interaction, it gains energy and angular momentum. And incidentally, nothing is coming out of the black hole. We're not violating causality or any of those properties, but the energy and angular momentum in a black hole space-time is in the whole space-time. It's not localized to it inside the horizon. So the energy angular momentum of rotation can be extracted from black holes. And incidentally, that's also consistent with Hawking's area theorem, where any interaction with a black hole, the area increases. Because it turns out that if for a given mass, the black hole with the largest area is a non-rotating Schwarzschild black hole. So rotating black holes actually have smaller area, so you can extract energy. They grow as they spin down to a Schwarzschild black hole. So the process that I'm going to describe, at least I'm going to describe two flavors of the superradiance. One is scattering a gravitational wave of a black hole, and another is sort of a a matter field which is confined to the black hole, and this extraction can actually be unstable, and it can cause sort of clouds of these bosonic fields to grow around the black holes. So the former, scattering a gravitational wave, that's purely of theoretical interest. And there's some example, well, I'll show you in the example especially why I think that this might still be a very interesting problem to pursue just from a theoretical physics perspective. But it's not likely that there's any scenario in the universe where large gravitational waves fall onto black holes. So it's not astrophysically relevant. The case of these, the bosonic fields, there's suggestions that there might be ultralight scalars, particles in the universe, so the so-called string axiverse. And the idea is if there are particles with masses where their Compton wavelengths are comparable to the size of black holes, this mechanism could operate and naturally spin down astrophysical black holes. So if black holes are formed with the same wavelength as these fundamental particles, eventually we shouldn't see any spinning black holes. So there's an astrophysical application to that. Okay, so what are the open questions with black hole superradiance? And I was thinking scattering a gravitational wave of a black hole. And it's something that's been known for a long time, 30, 40 years at least. And so though, until these simulations that I'll show you, no one has really looked at the study beyond sort of linear perturbative order. So the first thing that we wanted to do was just a sanity check. Is energy momentum conservation, does it all work out as it should? And of course it does. It's not that's not going to be a surprise. But what we were actually more interested in, it was this phenomena beyond the linear regime. So if we have a very large amplitude gravitational wave packet that contains a significant amount of energy, and if it's so how is that going to interact with a black hole? Because there's still this question of cosmic censorship that Powell sort of spoke about and sort of showed conclusively that it doesn't work in higher dimensions. It seems to hold in four space-time dimensions, but we're not sure. There's no proof of cosmic censorship. There's no proof that there can't be some interesting nonlinear interaction that could happen where a naked singularity doesn't form. So before we had the solutions to the binary problem, and Deirdre showed that very freaky little graph that Kip showed, for the merger regime, another possibility was, and no one knew at the time, that actually the merger of black holes might result in a naked singularity. So empirically now we know it doesn't, but there's no proof that cosmic censorship is satisfied. It's just all these anecdotal examples. And perhaps from a sort of more physics perspective, cosmic censorship doesn't really, there's no reason why it should be satisfied. It doesn't seem, to me it's almost like it's an unfair principle if it holds, because relativity, singularities that form in a theory tell you that you've reached a regime where that theory is no longer valid and a new theory has to take over. And so we should be able to see phenomena where that's happening to give us clues about what's going on. And so with general relativity, naked singularities would be clues to what quantum gravity is. So why is nature so cruel as to hide all clues about quantum gravity from us? Is there some astrophysical process that could produce a naked singularity? Well, it won't look like a naked singularity. It would look like some beyond GR physics, but that would be something interesting. But unfortunately, it seems like 4 dimensions we're censored. But so part of this problem is, can we somehow break this conjecture? Can we come up with something where we might violate cosmic censorship? And I'll show you, you'll see how suggestive or not it is, but it might be that in the limit of extremal black holes, superradiance scattering, that might be a way to get cosmic censorship violation in 4D gravity, though it's probably a set of measure 0 in a sense. Okay, so what is the problem studying superradiance? And well, so from the numerical perspective, and I'd say in some aspects of it has already been studied, in particular with an analogous charged black hole system. So you can also get sort of the similar effect of charge of superradiance with black hole charge. And the nice thing about that case is that the charged solution in general relativity is spherically symmetric, and so you can actually study charged superradiance in spherical symmetry. And Louise Lehner, amongst other people here in the audience, have looked at that before. The problem with the Kerr case, so even though the Kerr solution is axisymmetric, so you think, okay, that's not that bad. An interesting property of gravitational waves in general relativity is that axisymmetric gravitational waves don't carry angular momentum. So to get this superradiance scattering, you can't rely on any symmetry. So it's a full 3+1 dimensional problem. There are other problems with the matter superradiant, this Broca field superradiance that I'll mention. Oh yeah, I think I'm mentioning it right here, right? So okay, so the complication with the Kerr case is, okay, it's a full 3D problem, but you think, okay, that's not too bad. We do 3D mergers of Kerr black holes, but to actually to see sort of a significant effect, what you have to really do is you have to be very close to what's called an extremal black hole. So the black hole is rotating close to the maximum possible in general relativity, and it turns out that there are complications the higher the spin that you try to get. And it's perhaps not too surprising because you can write the Kerr solution with any value of the spin parameter that you want. So we usually use a normalization where a spin of 1 is so-called extremal, and anything greater than 1 is a naked singularity. So you can imagine if cosmic censorship is preserved, there's going to be some physical reason why it's very difficult to get that limit. And for some reason, it's very challenging to actually simulate black holes with very high spins, so 0.999 in the spin parameter. So it's not such a long simulation, just order 100M, but that aspect is challenging. With the matter fields, so perhaps let me just in words explain what the thing with matter superradiance as opposed to the gravitational case. So with the gravitational case, we're going to scatter a gravitational wave off and see what comes back out. So one thing that's interesting, if you could somehow put the system in a box, say if you could have reflecting boundary conditions for the gravitational wave that you can't, this might be a runaway process. So you extract a little bit of energy, it comes back out, it reflects off the boundary, it goes back to the black hole and it grows, and then you could get, well, I guess what Tucholsky called back in the 70s a black hole bomb, where you can extract 20 to 30% of the energy of the space-time in via this mechanism. So again, you can do that with gravitational waves, but now with a massive field, like I mentioned, one of these ultralight scalars, that's effectively got a potential where you can set up a configuration where the field is essentially confined to be around the vicinity of the black hole. So the field can escape to infinity. And so naturally, the nature of the potential, of the mass term in the potential, allows sort of this black hole bomb scenario to be realized. And so that's that's the mechanism of why, if you had these ultralight scalars, just a seed quantum perturbation, if you will, can extract a finite amount of energy from the black hole over a certain amount of time. So it's initially an exponential growth. The problem with these Proca fields is, or with any of these fields, is the time scale of that growth is incredibly slow, especially compared to gravitational waves. And so a Proca field is it's a massive vector field. The complex thing is a trick that we use to use an axisymmetric simulation that I'll mention in a second. But the time scale for these things can be astrophysical. So in other words, you have a stellar mass black hole with a light crossing time scale is milliseconds, but it might take a gigayear for this cloud to grow and extract all the energy of it. So what we did is we chose this massive vector field because it's got the fastest growth rate, but still we had to fine-tune the parameters such that we only needed order 10 to the 5 m evolution to see this thing grow. But that's a computational challenge with the massive superradiance. Okay, on the other hand, in both of these cases, sort of the dominant piece of the space-time is the Kerr solution. So even in the most optimistic case, say with the massive superradiance, we might extract 10% of the energy. As you'll see with the case where we scatter a gravitational wave off, that gravitational wave will also have about 10% of the mass of the space-time. So it's very massive, but still 90% of the mass is in the Kerr black hole. And the thing with the Kerr black hole is we know the solution exactly. So it almost seems silly that we have to use extreme computational resources for something which might just be, at the end of the day, might just be a perturbation of Kerr. So one thing you could say, well, okay, if we really want to study this problem, well, let's write a code that's adapted to the Kerr solution. Let's define a metric that's a perturbation away and evolve variables which are these perturbative variables. And yes, that might be a way to do it, but we were lazy. So we had this Cartesian code that was developed, that worked with the binary black hole problem, and said, can we actually take advantage of the fact that we know the Kerr solution with this Cartesian code? And that's when we sort of, Will East and I came up with this background error subtraction technique. And essentially what it allows us to do is completely under-resolve the Kerr part of the solution, because what we can do is with whatever code you use, in this case a Cartesian harmonic code, we can compute the truncation error of that exact solution and subtract it off the solution of whatever nonlinear problem that we're interested in. So let's see, I'm doing on time. Okay, I'll very briefly, excuse me?
There's half an hour.
Okay, so I'll just very quickly go over Perhaps another example was actually the motivating example, but that might also perhaps illustrate this issue a little bit more clearly than what I've mentioned before, especially if you don't know the curve solution, sort of and what the problems with near extremal are. So this was, so at the time we were interested in looking at tidal deformation, or the tidal disruption of a star interacting with a supermassive black hole. So back then, this is several years ago, there were several candidate events that astronomers had observed that looked consistent, or that they could explain as massive, 10 million to 100 million solar mass disrupting a star like the sun. And actually today now with these transient surveys, there are actually many of these candidate events. And so the issue of computing, like what do you expect? So then Martin Rees back in the day, just with almost back of the envelope, sort of the leading order calculation of what you should expect. But an interesting thing in particular with these black holes is that if you look at the place where the star is going to become unbound, so away from the black hole, it's a self-gravitating object. It's holding itself together through, gravity. And eventually, it's going to get tidally disrupted. Once it's tidally disrupted, especially relative to such a massive black hole, you don't have to worry about how it never affects the supermassive black hole. It's such a small perturber. But then you can also not worry about self-gravity. But the interesting thing in these black holes is that the tidal disruption radius is very close to the innermost stable orbit of the black hole geometry. So the place where self-gravity of the star becomes unimportant is sort of on the verge where it's in the most interesting part of the black hole space-time. So you'd expect that strong relativistic effects might be visible in the spectrum of the disrupted star. And so the question is, how do you self-consistently take care of that? And the two approaches that people that use for that are sort of in two opposite regimes of approximation. So one is when the star is far from the black hole, you just use Newtonian gravity. And in some cases, you can try to mimic some of the effects of the black hole by using a modified Newtonian potential. So that's one option. You just use Newtonian gravity and a Newtonian star. And the other limit is once a star has been disrupted, again, its self-gravity is unimportant, and you can just use relativistic hydrodynamics on a black hole background. But then the question is a sort of intermediate regime, like with self-gravity still important near the Kerr black hole while it's being disrupted. How do you consistently compute what's going on? And so it was more, in some sense, I don't know how important taking care of all the fully relativistic calculation is going to be, but it was almost a theoretical question, like how do we do it self-consistently in a way which is not we try to come up with clever ways, and at the end we fail in the self-consistent way. Just solve the Einstein equations, right? That's what we want to go after. But this sort of illustrates the problem. So now let's say we wanted to do this self-consistently. So we have the supermassive black hole, we have the star. They're similar in size, but the problem is that if you want to think, the Newtonian potential of the star is 6 to 7 orders of magnitude smaller than that of the black hole. Or in other words, in a metric way of thinking, relative to Minkowski space-time, the metric near the black hole is an order 1 deviation from Minkowski, whereas the metric of the star is going to be an order 10 to the minus 6, 10 to the minus 7 deviation. But the star isn't going to affect the black hole at all. It's just going to sit there. It's going to have there's going to be no dynamics of the black hole. But if you want to solve the problem self-consistently, so we're solving for the metric is going to be the black hole plus something that's 10 to the minus 6, 10 to the minus 7, and that's where all the interesting behavior is. So we'll need a code that's so accurate we can resolve this black hole region of the metric to within 7, 8, 9 decimals, which is just completely crazy with finite, our fourth order finite difference scheme on Cartesian grids. And so again, let's say one option, write a new code that's completely adapted to the stellar problem where you can somehow analytically factor out the black hole. But then we realize, well, we know the solution exactly. We can let the computer do it for us. And so the idea is, so we're going to take this, we're just going to do the problem brute force, but then without the star, we know what the exact solution is. We're going to feed that through our computational code, get the truncation error from that, and subtract it from the problem. And that's basically this algorithm. So it's incredibly simple, but I think, and unfortunately, there are not too many problems where it could be used, but where it can, like in this and the eventual superradiance, I think it works like magic. So hopefully there's some problems that you're interested in where something like this could be applied. And incidentally, it's not geared to finite difference, pseudospectral, any kind of discretization scheme. In principle, this would work by. So let's imagine that the solution we're after contains, something, capital Y, where we know the exact solution plus something else, this delta. And you're saying delta doesn't have to be small, doesn't have to be linear. And you don't need an analytic solution for Y, as long as you can compute it efficiently to within, say, machine round-off. So if you can integrate some ODEs to get your exact solution, that's fine. So now we've got some evolution operator that evolves our equations from time step n to n plus 1. So what we do with this algorithm is first we just take on whatever background, whatever mesh structure you have, you evolve your exact solution one time step, and you compute the truncation error, because you know what the solution is at that advanced time step versus your discrete time step. Then you evolve the full problem, and you just subtract the truncation error. So in the limit of infinite resolution, we're doing something which converges away. Right. So a couple of comments. But I guess I just said that. So it converges away. So we're altering the equations at the level of truncation error. So we're not really changing the equations. The other thing is this is correction. I've written it as a delta, but it doesn't need to be small or linear. In fact, it can be anything, And it might be like in some problems, you might start with something where this delta is small, but perhaps it becomes a dominant part of the solution. It doesn't matter. There's nothing about this being small that's relevant in this algorithm. Okay. So the other thing that's nice about this is it's trivial to adapt any code to this. As I said before, like one option in treating problems like this, where you perhaps know what the exact solution is to write code and variables that's adapted to the problem. Like a black hole, you wouldn't want to use Cartesian coordinates. You'd want to use sort of spherical polar coordinates. You might want to use variables that are perturbations of the curve, even if you want to solve the full nonlinear problem. But this says you don't have to worry about that at all. Just take your code, whatever coordinates, whatever discretization method, and it's fine. All you have to do to modify it is every time step you do it twice. Once with this background solution as initial data, and then once with your full solution, and then you subtract the truncation error. So in some cases, like with the Kerr case, the background is static. So it's not necessarily as inefficient as having to do it twice. You can get away with it with evaluating this much less than that. But essentially, what it buys you.
Do you choose then here the gauge source functions to impose that the solution in the background is explicitly time independent?
No, it can be time dependent. And in fact, what.
I mean, in this particular example, did you do that?
Yeah, so in one example I'll show you, we did it. So we just did the head-on case, and Will actually did a full 3D case. But then what he went to the the center of mass frame of the star, and so the black hole was actually orbiting around the star, and so it was actually a fully dynamical solution, and it was. Again, it's like with a Kerr solution, you pick. I think we picked Kerr shield, so there are source functions with Kerr shield and that are dynamical. So everything, the metric, your gauge evolution. If you can have the exact solution for that, which we could with Kerr, then that goes in this first step. And then in the second step, if you have a dynamical gauge that's even different from the gauge source functions that you use, that's fine. It doesn't matter. So in the worst case, if you do something where the actual representation of your solution is completely different from your exact solution, it just means it's going to be you getting nothing out of the algorithm. But it's still truncation error that you're changing it by. So essentially what it does at the end of the day is it allows you to significantly under-resolve the part of your solution that's dominated by the exact solution. Okay, let me just for time, let's skip this. So that is showing this. There is a regime in this problem where it does help. But this perhaps is one example to show. So this was a case of a star. There's the black hole. There's the star, axis symmetry. So this is the symmetry axis. So once we run this, the star would fall into the black hole. And so we used finite difference, mesh refinement, and you can see we and in this algorithm, we also didn't even have to change the truncation error estimation procedure. So we said we want to evolve this. This is with this background error subtraction. Give us the grids that we need. And you can, I'm not showing it here, but you can sort of see like little edge effects that we get. So we had this box-in-box refinement. So it was resolving the star. Here's the black hole. So the black hole is completely under-resolved. But it doesn't matter. Its truncation error is negligible if we subtract it. And this, just to compare, this is the example if we didn't use this algorithm with the same grid pattern. You can see there's a huge truncation error that's coming from the black hole. So essentially, if we had just fed this through the usual algorithm, it would have set many refinement levels around the black hole to get to the requisite truncation error. Here it's saying we don't need to resolve the black hole at all. So in this head-on case, we got a speed up of about 40 times relative to the unresolved case. There's a cute little animation of it again. So Will did a full 3D calculation. So we couldn't actually do this without this background error subtraction. It would have been too expensive. But we estimate we got about a factor of 100 increase in speed up. So the background is just artist thing. There's the black hole, and here's a star coming towards the black hole. And in this case, he chose an impact parameter where it would be. So there it comes, and it just gets swallowed by the black hole. So that was a few 100,000 hours of CPU time. Not interesting, but it would have been tens of millions if we hadn't done this. And of course, it's with this problem, you might say perhaps you could have gotten away with some modified Newtonian potential of a black hole. That's fine, but it was more again, it was actually more, even was motivated by astrophysics. It was more a question of can we do this theoretically. Okay, so now let me look at the scattering of a wave of a black hole. And again, this is a good application for the best, is because this background error subtraction technique, because we know what the Kerr solution is. And again, we don't have to write a new code that's specifically geared towards studying superradiance. We can just use our standard Cartesian thing. And it's a very, so the horizon is going to be this Lego sphere structure. The discretization error is large, but it's okay. We can get rid of a lot of it because of this thing. So this is this first application. So imagine we've got a black hole with mass, spin, and rotation speed, capital omega, and now we implode a wave, and we're going to decompose that wave into spherical harmonics. And for our initial data, we're going to pick some spherical harmonic component of the wave. It's going to implode onto the black hole. Some amount of the energy is going to fall into the black hole, but some of it will escape. And we want to measure what's coming out at the end of the day. So essentially, what is the ratio of the amplitude of this wave relative to the input? And so, as I said, it's been known for a long time that if you essentially, it's like that spinning wheel analog that you have. So this little m is the azimuthal wave number of that wave packet. Little omega is the frequency of the wave. Capital omega is the frequency of the black hole. So essentially, little omega over m is, if you will, the velocity, the angular velocity of this wave packet. So if that is less than the angular velocity of the black hole, it's like this wheel example. It's going slower than the black hole, and so it's going to gain energy as it scatters off the space-time. And so, like one of the questions that we want to ask, well, if we don't look at the linear regime, if we have a massive wave packet, so we sort of smack the black hole hard, is cosmic censorship unheld? Is there anything unusual going on relative to the linear process? So that was sort of the motivation. So the setup, just particular details. We chose a black hole with spin 0.99. Again, with the units we use, 1 is the maximal spin. So it seems like we're quite close, but in other respects, you have to get many, many 9s to really get close to extremal in relativity. And one estimate that tells you is, if we compute, at least in the linear regime, what omega m you need for maximum superradiance is about 0.75, whereas in the extremal limit it would have been 1. So in a sense, we're still relatively far from extremal, but we're close. Another interesting number is the so-called least damped quasi-normal mode of the black hole. As Deirdre sort of showed in her waveforms, that's sort of an interesting part of the mergers that we see. There's the in-spiral, there's a merger, and there's a quasi-normal ring down. And the one that dominates is the so-called least damped mode. It's an L equals M equals 2 mode. And that's its characteristic frequency for this particular black hole. So we scattered 3 classes of black holes with different amplitudes. One where the frequency of the wave was tuned to the superradiant frequency, one where it was this least damped mode frequency, and one where it was above the superradiant. So now it wouldn't be superradiant, but just sort of as a sanity check. And here's an animation through the equatorial slice of the black hole. So this Newman-Penrose scalar psi4 measures ingoing radiation. This one psi4 measures outgoing radiation. And so you'll see the wave sort of, sorry, one's a polar slice, one's an equatorial slice. And so this is just to demonstrate the wave is going in, and black holes, they don't suck everything in. That's a misnomer. So in this case, you can see that something isn't absorbed by the black hole, and it comes out at the end of the day. So there the waves go in, they interact with the black hole, and now we see the waves coming out. And this shows a kind of surprising phenomenon in relativity that gravitational wave fronts actually become square as they go away from the black hole. Okay, I'm glad a few people laughed that they're paying attention. No, that's such a wave fronts are spherical far from the black hole. This is an artifact of, we use a compactified coordinate system. So we bring infinity to a finite distance, but on a cube. So they're actually really spherical wave fronts, but in our coordinate domain, they look squarish. Okay, here's a more sort of fancy sort of artist's or a visualization person's rendering of that. Where now we're overlaying both the ingoing and outgoing radiation, but in blue and red. So blue is ingoing, red is outgoing. But the one thing that's sort of interesting thing about this, so is notice so that this white little sphere, that's the horizon of the black hole. So it's actually spinning, but the horizon is actually symmetric. So you can't see the spin there. But as this wave starts to interact with the black hole, and actually this is a case where it was not tuned to the maximum superradiant frequency, but the quasi-normal mode frequency, it will look like the black hole starts to spin. But actually what's happening is this is a massive wave. It's massive enough that it's deforming the black hole. And so now it's like a deformed shape, and so you can see the spin because it's deformed. So it's actually always spinning, but you can see the deformation then. Okay, so okay, there the wave comes in. Now notice, you can start seeing the spin. Now this is the wave coming out, and then eventually it settles back down to a spinning but stationary Kerr state. Okay, so what's interesting about that, so let me just first show, okay, the bottom line is, so do we get superradiance, do we not, what happens? And this is perhaps the easiest thing to show that we do. And this is showing the 3 characteristic features of the black hole. One is its mass, the other is its angular momentum, and this is its so-called irreducible mass, which is related to its area. So again, regardless of the interaction, the black hole's area always grows. But if it's superradiant, the mass and the spin should decrease. And you can see with the superradiant case here, that's these black squares. One was the initial mass. There's an interaction, and it ends up with mass that's less than 1. So the black hole lost mass, and it also lost angular momentum, even though the area increased. So the case where it wasn't superradiant, the black hole gained energy. So again, about 10%. So these are pretty massive wave pulses. So the black hole gained 10% of energy. It gained spin. But the case that's most interesting perhaps here, and like hinting to where there might be cosmic censorship violation, is actually the wave that was tuned towards the quasi-normal mode frequency. And at least based on this plot, this is sort of the mildest case. Yeah, there's some dynamics, but it gains a little bit of mass and spin, but not too much happens. But now if we look at what's happening with the geometry of the horizon, that's this large oscillation case, that's this resonant frequency. So what I'm showing here is sort of 2 measures of the intrinsic geometry of the horizon. One is the ratio of the proper to equatorial circumference. And this is sort of what you saw in that movie when you started seeing the oscillation, was the fact that it was becoming distorted. And here's just a measure of scalar curvature on the black hole. So the case which actually distorted the black hole most significantly was tuning to this quasi-normal mode frequency, even though it didn't interact that strongly in terms of energy exchange. So I think why I think this is an interesting problem, and I'm hoping people will add more 9s, even though that's going to be very difficult, is I think if there's a way to break a black hole in 4 dimensions to violate cosmic censorship, is I think it's sort of, it's driving it to resonance at this least damp quasi-normal mode, because in the limit of an extremal black hole, this actually becomes an undamped mode. But again, it might be a set of measure 0. It might be so difficult to get there. But I think that's where some very interesting dynamics might be possible with 4D black holes. Again, probably not astrophysically relevant, but interesting. Excuse me? Yeah, just is, yeah. So no, it's just the Gaussian curvature of the apparent horizon. Yeah, I believe. Okay, so I've got like 5 minutes or so. Yeah, so then just with superradiance again, it's this is perhaps somewhat less interesting in the sense that, so again with the scattering of a wave, it was, things were as expected at the linear level. But I think the interesting regime is what's hinted at in this, if we could actually go to extremal. With a massive particle superradiance, actually the end answer is kind of much less interesting than what you might have expected and what some people did suggest. So here perhaps the open question was, so again now unlike the case where we scatter a wave off, it reflects, it gains amplitude and it goes away, here we have a massive field. And so we excite a little perturbation. So there's a little bit of this field. It undergoes a little superradiance scattering. But now the mass confines it to the black hole. So it goes out. It's essentially it undergoes multiple scatterings. And each scattering, it grows in amplitude. And so at least at the linear level, there's exponential growth. So one of the open questions is, well, if exponential growth isn't sustainable, it's got to end somehow. How does it end? Does it end explosively with this black hole? Or is it always such an effect that you can look at some kind of linear approximation where you've got some amount of energy in this cloud that's grown over the past n folds, and then that is undergoing a little bit of a growth relative to the previous one? Or is there something interesting that happens at the nonlinear level? I'd say that there was, in the case of, again, charged superradiance, and this is what Luis had done, there was some indication that there might be a bit more of an explosive overshoot in this exponential growth. What I'll show you is, in our case, that we found with this Proca field is it's a very smooth saturation. So it grows exponentially, it saturates, and you're left behind with this cloud of energy around the black hole. So let me just not go over the details for now. I'll just show you the animation. Oh yeah, this is the system of equations. Let me just mention one thing that was another trick that we used to allow us to solve this 10 to the 5m time scale. So as I mentioned, gravitational waves can carry angular momentum in axisymmetry, so we had to do the full 3D problem. The same is true of these massive bosonic fields, as you need to break axisymmetry. But there's a trick that we can do with these massive fields. Essentially, we can superpose two of them together. So we can have two of these bosonic fields, but we make them sort of 90 degrees out of phase, because then it's the sum of the squares of these fields that are the stress energy tensor that go onto the right-hand side of the Einstein equations. So if you essentially have a field that's in a cosine configuration and one in a sine, cosine squared plus sine squared is 1. And so if you carefully arrange the phases of the two fields, you can have a rotating configuration that's actually axisymmetric from the space-time perspective. So the stress energy tensor is axisymmetric even though there's angular momentum. And the easiest way to do it is by just to use a complex field. So the real and the imaginary parts are those two fields. And so that's what we did. And so what it allows us to do is to actually use an axisymmetric simulation using this so-called cartoon mesh method that Deirdre mentioned, to solve a problem which is, at least from the matter perspective, is three-dimensional but on a two-dimensional grid. So this was a 2 plus 1 dimensional evolution. And I'll show you the animation, but as I said, it's very uninteresting. It's just what you expect. So there's the black hole, and this little sort of this fuzz around it, that's the energy density in this Proca field. And now it just grows. So this is in units of 10 to the 3m. And it's just getting larger in a very slow, measured fashion. And at some point, it smoothly saturates. And why it saturates is, again, you can think of this wheel analog. So we choose parameters where the rotation in this field is slower than that of the black hole. So it's sort of gaining energy, but the black hole is spinning down. And it saturates when the black hole is spun to the point where they're essentially in co-rotation. And so this plot is just sort of showing a measure of that. Sorry, this plot is showing how much energy and angular momentum growth we get in the field. So we get the initial exponential growth, and this is a smooth saturation, just with various values of these mass parameters. So that's sort of the smooth saturation. And again, perhaps the interesting thing from an astrophysical perspective is you can extract a lot of energy from these black holes. So at the end of this one case, almost 10% of the initial mass of the black hole was now in the scalar field, which is very significant. But this is what I mentioned before with why it stops. So again, this is the sort of the velocity, if you will, in the black hole in each of these cases, and this is the velocity of the field. And you can see the velocity, say in this case, of the black hole decreases until it matches that of the field, and they sort of in co-rotation on the horizon, and that's how it saturates. Okay, so to conclude, just to sort of summarize, I think the nice thing about the Einstein equations, in a sense, compared to other nasty nonlinear equations like Navier-Stokes, is we don't get shocks, discontinuities, other weird things like that, not weird, other unusual phenomena like that, or turbulence where you've got this cascade. At least in 4 dimensions, we don't see that. We have singularities, but we can deal with them. But that means that, in some sense, we've been able to get away with using, high-order finite difference or pseudospectral. And I guess high-order, in the community is between 4th and 8th order. And I guess in many applications, they won't consider that high-order finite difference. So moderate-order finite difference and pseudospectral methods have been efficient. And I didn't say much about matter. But of course, if you add the right-hand side, then you have to deal with all of those complications. But an interesting thing, again, with Einstein gravity, and if you will, it's almost it's because of the equivalence principle in a sense that it doesn't matter how nasty it is, if you can get the evolution of that matter working in special relativity. So you have to take relativity into account, but if you can get it to do it in special relativity, there are essentially not going to be any obstacles lifting it up to a general relativistic code. At least if you can do it in special relativity in arbitrary coordinates, in curvilinear coordinates, then there's no problem in doing it with matter. In terms of, again, open problems, I think this has sort of been a theme of today's GR talks, is the length scale issues. I've mentioned this best thing which can help with a couple of orders of magnitude in a very restricted region of solution space where the solution is dominated by a known solution. But for other problems, like this extreme mass ratio problem that Deirdre mentioned, I think we need new ideas. Best is not going to be good enough to help out there. And again, if you look, think of what we need, Moore's law is also not going to help. If we want to have these extreme mass ratios, for example, templates by the time Lisa flies, and if we'll need it for Lisa, that's perhaps 10, 15 years of Moore's law. That's not going to give us 3, 4 orders of magnitude of extra cost, even if we can take advantage of it. So we really need new ideas. Thank you. Yeah.
Maybe I sort of misinterpreted it, but there's some time here where it's not monotonic.
Oh, sorry.
Any interpretation for that?
Yeah, cosmic censorship is being violated. This actually goes to like Power's point about sometimes finding apparent horizons is a pain, and here our apparent horizon, the apparent horizon is struggling to resolve it, and so we get some jitters there. But yeah, that's. And incidentally, that's why, like this was really interesting. So one thing we said, well, can we try larger amplitude waves, even if we don't go to higher spin? And this 10% of the mass of the space-time was as large as we could go essentially because of these problems. That the distortion in the horizon became so large, our apparent horizon finder failed. And
I mean, I've seen some situations in my own knowledge where sort of the apparent horizon goes out fast and then jumps in, but here it looks like it's really coming in smoothly, right?
Yeah, so it's especially if in convergence suggests that we are solving the Einstein equations exterior, so this has to increase. And so if this is sort of now at this point it's settled down already. So this is kind of, I think, this is correct, that's correct, and it definitely can't go up, it can't go down. So the real solution, at least in terms of this this is a proxy for the area, must be connecting those. And yeah, the coordinate shape could be doing crazy things, but we lose.
It was like an event horizon versus apparent horizon type of question.
No, and I think like in this situation, you're going to use a dynamical horizons framework. So we use that to measure these quantities of the apparent horizon. But I think there's an equivalent theorem that says that in this case.
If the tube is like smooth,
Right.
it can jump.
Right. Yeah. So like yeah. So there are some technical outs, but I suspect in this case it's not a event versus dynamical horizon thing.
So that means that there were errors there that are at least 5 or 6%.
Not errors. So one thing, and perhaps I don't know if perhaps in relativity we find that obvious, so we almost don't mention it, but we don't put black holes into this simulation. There's no surface there. Space-time is sort of smooth as far inward as we want to go, and at the location of the horizon, nothing weird strange is happening in the metric. It's just a piece of space-time, and that's also the equivalence principle in some sense. That if you were small relative to the radius of the curvature of the horizon, locally it's going to look like a piece of flat space, Minkowski space to you. So what we do is we start with initial data where we know they're black holes, and then afterwards we try to find them. And so that error there is our apparent horizon finder. So the space-time goes inside it. We use excision, so there's a surface that we excise. We're not getting anomalously large errors there, but at some point our post-processing that's trying to find the horizon is failing. At least it's not completely failing. It's becoming unstable. And why that is bad eventually with this excision strategy is we use that to guide where we excise. So when we lose the horizon, even though it could evolve for a while, if we needed to adjust that excision surface, we have no guideline about where to do it. And that's why sometimes the code crashes. It's essentially the horizon would move into what was previously excised. So in principle, we never, we can get evolutions. We don't even have to know where the horizon is. It's not something that is obvious, but we have to search for it. And that's the problem there. So it's with the horizon and not the solution.
But how do you put error bars on your computation?
Oh, so we do truncation error estimates. So we multiple resolutions, convergence studies, sort of assume or check that we're getting like 4th order convergence, and then using multiple resolutions to put error bars on things. And so here, I forget what the errors were in these quantities. Like when we didn't have problems with the horizon, but it's less than so in terms of the total mass of the space-time of unit 1, it's less than I would guess, if I'm remembering, like a 1/10th or 100th of a percent. So it's quite small in this case.
In the metric.
Or in the asymptotic values. So of the quantities left. Yeah, in the metric. I mean, we're getting 4th order convergence. I'm not sure, like relative to say a unit value of a metric. I don't recall now what the errors were.
You think the metrics have 2-3 decimal places to add?
Well, in this case, I would say probably at least 2 decimals, which is sort of good enough for this, especially to this case. So the difference in this case between this and the star case. So in the star case, we needed 7, 8 effective decimals for the star, but then we just adapted things to the star and we ignored the black hole. In this case, we're actually perturbing the Kerr black hole, well, not perturbing it by something that's of order 10% of the black hole. So it's a very large perturbation. So in some sense, like what this helped was to deal with issues of putting a near extremal black hole on a Cartesian grid which wasn't adapted to the structure of the horizon. So that by itself, so just the Kerr black hole without any perturbations is large error. But then this best sort of got rid of it. And so essentially what's left over is a nonlinear interaction between the wave and the black hole. And I think that's quite good. That's less than 1%. Roughly that order, if I remember.
Other questions? Okay, so